Question number 11, it's based on chapter 4. Okay, chapter 4 distribution. So I think I told you this. Please check all the distributions in chapter 4. Okay, here I have covered I think only two distributions, normal distribution and this one, it is exponential distribution. Okay, so I have covered only two, but you have to check all other distributions. Okay, uh, question types from any other distribution is very similar to this one. Okay, so okay, let's do this one. This asks expected value of x, so you should know what is the expected value of uh, exponential distribution. So first I'll write here the distribution of simple f x lambda, distribution of exponential distribution. X has a exponential distribution with its parameter lambda. This is the parameter for exponential distribution. So it is 2. Oh, it is 2. Okay, so we can write it like always exponential distribution exists for greater than 0. Okay, so in general exponential distribution is lambda e to the power negative lambda x. Here it is x greater than or equals 0. So same here, x greater than or equals 0. Otherwise it is 0. X less than 0, our distribution is 0. So this is the exponential distribution. Actually we write only the first one because for the exponential case we consider x greater than 0. Okay, so okay, we need to find expected value of x. So expected value of exponential distribution is 1 over its parameter. Okay, this is your lambda. Lambda equal 2. So 1 over 2, which is 1/2, 0.5. Variance of x. For variance of x, 1 over lambda squared. 1 over lambda squared means 1 over 4. Okay, 0.25. So this is your variance. This one done, this one done. This asks probability of x less than or equal 4. So everything, x start from 0, 0, 1, 2, whatever. Okay, let's say 4 here. So you need including 4, whatever this side. Okay, you need the probability of this from 0 to 4. Since this is a continuous case, you can use your integrals. 0 to 4, okay, exponential distribution, lambda e to the power negative lambda x dx. We can rewrite this, plug the values. Lambda means 2, e to the power negative 2x dx. Okay, so simplify this one and you will get 1 minus 0.00 I think 304. So answer going to be 0.9996. 1 2 3 4, yeah, 996. Okay, same thing you have to do. Next one asks probability of x in between 1 and 3. So 1 is here, 2, 3, including 3 and 1. Including or not including doesn't matter because this is a continuous case. Okay, so you have to get this probability. 0 is here, so whatever this side, x values. Okay, you need to get this probability. To get this probability, again you have to integrate within that interval. So 1 less than or equal x, greater than or equal x, less than or equal 3. Which means your new boundaries are 1 to 3. Okay, 2 to the power 2 times e to the power negative 2x dx. Again you have to do this integral this becomes negative. This becomes negative e to the power negative 2x 1 3. This becomes 0.1328. 1328. Okay, 1328. Meantime, if you have any question, please ask me. Okay, don't wait until the last minute. Just point out to a question at that point. Okay, this is the fourth part. Yes, we have done all four: expected value, variance, probability in between two values, something less than, something in between. Okay, this is how we deal with distributions. Main thing is you should know what are the variance and expected value of those distributions. Otherwise, you have to figure it out using, since these are it's a continuous case from negative infinity to positive infinity, their distribution lambda x x times their distribution. Do you remember that dx? This is how we find the general expected value. So you have to use this to find the expected value in general. Okay, we figured this equation 1 over lambda using this. Once you do this integration, you will see this answer is 1 over lambda. Okay, if you don't remember what is exactly for those expected value, then you have to calculate it like this. Okay. Question number 12. This is based on chapter 6. This is chapter 6 question. Let me check the chat. Oh, we don't have any chats. Okay. This question based on chapter 6. They have mentioned there is two population. Sorry, population 1 has normal distribution. Okay, let's say population 1 is capital X. Has normal distribution with population mean mu1. Okay, standard deviation sigma. Okay, let's say sigma squared variance. Okay, population 2, I'll consider it as y. It has also a normal distribution with mean mu2, and standard deviation sigma. Standard deviation sigma, I'll write it as variance sigma squared. Okay, consider that sample 1 is taken from, okay, sample 1 is taken from population 1, okay, which has a sample mean x bar and standard deviation S1, sample standard deviation, and also with sample size m. And sample 2 taken from population 2, which has sample mean y bar, sample standard deviation S2, and sample size n. Okay, those are the details that we can take from the take from the question. Okay, so let me draw this picture for you. Okay, this is your population 1. This is my population 1, and this is my population 2. Mean mu1, standard deviation sigma. Mean mu2, standard deviation sigma. From this, I have taken a small sample which has mean x bar. This is sample 1. Mean x bar, sample standard deviation S1, and size is m, right? Another sample from the population 2 is called sample 2. It's like this. Sample mean is y bar, sample standard deviation is S2, and sample size is n. Okay, based on these two, first of all, before I go to the part A, I can write something like this. Consider first picture. I can write expected value of x bar, right? Expected value of x bar is an unbiased estimator for mu1. right? We know that. I have mentioned when we are talking about this unbiased estimators. Okay, so expected value of sample mean. Okay, I'll write it here. Reason: expected value of sample mean equals to population mean. Population mean. Okay, so from this picture too, you can do the same thing. Expected value of y bar, you can write its population mean mu2. Clear? Uh, so what about variance? Expected value of S1 squared. Oh, sorry, this is squared. Expected value of S1 squared. It equals to sigma squared. The thing is, again, expected value of S1 squared, sorry, it is not x1, in general, sample standard deviation. Sample standard deviation equals to population sample, no, sorry, this is sample standard deviation or sample variance. That's fine. Population standard deviation. Standard deviation. Okay, it doesn't matter variance or standard deviation, both are similar. Okay, uh, I know that this is some kind of bias estimator. Okay, S1 expected value of S1 squared is not exactly sigma squared, but we consider it as a estimator. Okay, so same here, expected value of S2 squared equals to variance sigma squared. Okay, let's check what are the variances. Variance of x bar. What is variance of x bar? It is variance of x bar is S1 squared over its sample size M1. Okay, the reason is variance of summation I from 1 to n xi over n, right? This is what you have to calculate. So 1 over n become like n squared variance of summation xi. I did this one. Okay, once you simplify this, you will get this results. Same here, expected value of y bar, you can get S2 squared over, here sample size is n. Okay, okay, now you have these results. Now you have these results. Let me box these results because I need this result later. Okay, this one. Clear? Now let's go back and check what we need to find. First part A, show that x bar minus y bar is an unbiased estimator for mu1 minus mu2. Okay, if you need to find unbiased estimate, if you need to show something is unbiased to something, part A, you have to do like this. You have to show that expected value of that parameter, okay, whatever they ask, equal to what they have given, expected value of what they have mentioned. Here x bar minus y bar. Expected value of x bar minus y bar equals, here is mu1 minus mu2. Mu1 minus mu2. If this is true, okay, if above equation or formula is true, then you can say that, okay, then you can say that x bar minus y bar is unbiased estimate. X bar minus y bar is an unbiased estimator for mu1 minus mu2. Okay, This is what you need to show. Actually, you need to show this one. Okay, let's check this one. Expected value of x bar minus, y bar. Okay, you know x bar and y bar in this question they have mentioned population 1 and population 2 are two separate populations. Okay, so sample, this sample 1, this guy, sample 1 and sample 2, they have no relation. Okay, so you can consider they are independent. So expected value of x bar minus expected value of y bar. The reason is samples are independent. Okay, so what is this? From above, you can find expected value of x bar. It is mu1. From above again, you can find expected value of y bar. See, expected value of y bar is here. It is mu2. So without any problem, you can write this equals to mu1 minus mu2. So you have shown what you need. Okay. Finally, you can say, okay, since this equals to this, x bar minus y bar is an unbiased estimator for mu1 minus mu2. Okay, okay. Part B. Oh, you have to show this giant equation. Okay. Sigma hat squared is this one is an unbiased estimator for sigma squared. Okay, you have to do the same. You have to follow the same procedure. So expected, you have to show expected value of sigma hat squared, which means expected value of that giant formula n minus 1 s1 squared plus n minus 1 s2 squared over, so this is 2 over m plus n minus 2. This equals to sigma squared, right? So this is what you need to show. Okay, let's start from the beginning. Expected value of this one, m1 m minus 1 s1 squared plus n minus 1 s2 squared divided by m plus n minus 2. Okay, so this denominator is just a number, right? So it has nothing to do with expected value. Simply you can take that guy out from the expected value, plus m minus 2 expected value of times expected value of whatever you have inside the brackets, s1 squared plus n minus 1 s2 squared. Okay, again these m minus 1 and these n minus 1, they are just numbers. Okay, they are just numbers, and s1 has nothing to do with s2. They are independent because those samples are independent. You can rewrite this 1 over m plus n minus 2 times expected value of, okay, let me put this bracket here, expected value of m minus 1 times s1 squared plus expected value of n minus 1 s2 squared. The reason is samples are independent. Okay, now again you can simplify this again, 1 over m plus n minus 2 times this expected value, first part you can rewrite this m minus 1 is just a scalar, so m minus 1 take out from the expected value of s1 squared. Okay, here as well n minus 1 times expected value of s2 squared. Okay, So this becomes, let me put this bracket, m minus 1 times expected value of s1 squared plus n minus 1 times expected value of s2 squared. Don't worry about the brackets, which bracket is, whether it is a square bracket or curly bracket, it doesn't matter. Okay. Okay, now you can check what is this guy, what is this guy. Go back to that equations that we get from the very beginning. Expected value of S1, it is here. See, it equals to sigma squared, and same here, expected value of S2 squared equals to sigma squared. So without any problem, 1 over m plus n minus 2 m minus 1, you can replace this guy sigma squared plus n minus 1 sigma squared. How? From let me get this number 1, sorry, let me get this okay, let me get this number 1, this one. I'll consider this as my number 1, okay, equation number 1 or whatever. So from 1 mean, from 1 what we have taken in the first place. Okay, now almost done. So 1 over m plus n minus 2 times what you have, you can take out sigma squared, okay, because it is constant, it is the same for these two. This becomes m minus 1 plus n minus 1. So you can see you have sigma squared m plus n minus 2. Inside you have m plus n minus 2. This cancel with this, so you have sigma squared. Okay, so you have done. That's you have to show. Once you show this, then that's the answer, because this one right here, we are starting from here. We need to show that this guy, whatever inside the expected value, is unbiased estimator for sigma squared. We solve it, then we finally prove that that equals to, that expected value equals to sigma squared. So easily we can say that it is the unbiased estimator for sigma squared. Okay. Question number 13. I'm not going to, I think, yes, I'm not going to do all the questions, because last few questions, they based on chapter 7, 8, 9. Since I did more questions from chapter, especially chapters 8 and 9, I'm not going to do more questions from that. So please check last few questions. I'll try to do what I can today. Okay. So question number 13, this is chapter 7 question. You have to find intervals significant for this significant level. What is the hypothesis testing and prediction interval? Most of the time, prediction interval doesn't it doesn't come with individual question. Okay, it is like a question based on a hypothesis test. It's a part of the hypothesis test. I told you in the lectures how it looks like. Okay, so this is that kind of question. This is mix of chapter 8 and 7. Suppose you randomly select 8 participants. Okay, 8 participants. This is your n. This is your sample size who took an IQ test and record their scores. Okay, sample mean x bar. X bar given standard deviation, sample standard deviation given here. This is your x bar. This is your s. Assume that the population is normal distributed. Okay, population is normal distributed. Now you should know what kind of test is this. This is what? N is 8. And also there is an assumption population is normal distributed. So this is going to be T test using T table. Okay. So part A asks, part A, this is simple A. they believe that, okay, the true average IQ is greater than 90. So you have to check this, do the hypothesis testing at 5% significant level, which means alpha equals 0.05. Support their belief. Yes, you have to check this. So your H naught is always equals mu equals 90. Your HA is what? Greater than. So mu greater than 90. This is a right tail test. One tail, right tail test. Okay. Okay, let's conduct this. This is a t-test statistic because this is based on t distribution. You know why? The reason is number of sample size is 8, is small. So equation is x bar minus mu naught. Okay, mu naught is this value, mu naught. We always assume h naught is true once we are solving this square root of n. So plug the values, 98.6 minus 90. SS is 22.5 over square root of n, square root of 8. So this equals to 0.8. You need degree of freedom as well. Degree of freedom equals n minus 1, which is 7. So go to the table. They haven't mentioned which method you need to use. It is easy. Just pick whatever you want, either critical value approach or p-value approach. Okay. So if I pick p-value approach, okay, just a change, just p-value approach. This is a right tail test. You have distribution like this. This is what they have mentioned. This is our value is 1.08. Okay, our t value, t-cal, let's say t-cal. You have to find p value. So once I get the p value, you have to go to the t table and find where is this value. Okay, using rows and columns and also degree of freedom. Okay, you need this degree of freedom. Get the value, get the probability. That probability equals to 0.158. Okay, so you can see that your p value, what happened? P value, this is your p value. Your p value is greater than alpha or 0.05. Okay, it's greater than. So this one. So we do not reject our H naught. I'll write this conclusion for this question. So we do not reject H naught. The reason is we do not have enough evidence to say that the researchers say that what true average IQ, true average IQ score is greater than 90. Clear? This is a part A. So once we move to part B, it says that, let me check the time. Okay, it is 33. I have time. So part B asks construct 95 prediction interval for 9% IQ level. Okay, that's another case. 9%. So once we add another, once we need to predict the next person's IQ level, we just need to find the prediction interval. Okay, if we know the prediction interval, we can say, okay, 9% IQ level definitely inside this interval. Okay, that's the purpose of prediction interval. That's why we call prediction interval. So to find the prediction interval, once you check chapter 7 notes, you will see that, okay, prediction interval x bar plus or minus, okay, using this by multiplying, multiplying, this is like cross multiplying, you can get this formula, okay. T, since this is interval, always alpha over 2, this is your degree of freedom, okay, times S times square root of 1 plus 1 over n, 1 plus 1 over n. This is the equation to find the interval, plus and minus. There are two values. So simply you can plug the values. X bar is 98.6 plus or minus. T alpha over 2, degree of freedom is here 8. Degree of freedom is 7 and minus 1, 7. So alpha is 0.05. Alpha over 2 is 0.025. Okay. So based on that, go to the T table and find this value. Okay, this value is 2.365. Multiply by S, 22.5. Inside the square root, 1 plus 1 over n is 8. So once you simplify this, you will get 98.6 plus or minus 56.44. So your interval is 42.16 and 155.04. This is your prediction interval. Whatever comes next, ninth observation, it definitely lives inside this range. Okay, that's the purpose of prediction interval. I think that's the two parts. Yes, it's the two part. Do I have enough time for? Yes, I have enough time. Let me check the next question real quick. Okay, I think I can do the next part. Yes. Yeah, I can do the next one. Question number 14. Question number 14 is okay. Random sample of 550 recent donations at book levels that 82 were type A blood. Okay, this is, I think, okay, this question I think I did in the, this very similar question I did in the not last week, week before last week. Okay, I covered this very similar question. I covered a similar question. Similar question when I do the chapter 8-9 questions. Okay, question or question review, whatever. So please check that when you can find this. Then can we? Okay, I think I can move to question number 15. Just to, it's a little bit different. This is based on two sample t-test. Okay, this is two sample t-test. Question number 50, two sample t-test. You can see there are two samples here. So most frequently weight bearing joints such as during okay, youngest adult. These values are given. Let's say sample mean this sample size is n. This is n1 and this is n2. Okay, sample mean is x bar. Let's say this is y bar. I'm taking these notations, these letters to reduce the complexity of this problem. So this becomes my S1, this becomes my S2. Okay, all are based, all numbers based on samples, right? So sample mean, sample standard deviation, sample size. Assume that both distributions are normal with different population variance. Okay, check this one. They are normal distributed. Okay, different population variances. So older, it has normal distribution with mean whatever, I don't know, mean 1 with sigma 1 square. Okay, sigma 1 square. Younger, it has a normal distribution mean mu2 sigma 2 square, something like this. Okay, population. So we have taken samples for this. So since variances are different, population variances are different, this is a two sample t-test. Okay, unknown variances are unknown, population variances are unknown, they are different. So and also n1 and n2 are less than 40. Okay, so I'll write it here, n1 comma n2 less than, sorry, n2 less than 40, and population variance, population's variance is unknown. Population's variances population variances are unknown, sorry, both two variances are unknown, and same at the same time, and they are different. They have mentioned they are different. Okay, this is the key. So carry out the test of hypothesis this significant level to claim that to decide whether this one such as claim. So let's start from this. I'm taking mu1 as average AVG stance duration of elder, stance duration, check the time, it's 41, duration of older, not elder, older. So mu2, I'm taking same thing of younger. Okay, okay, two sample t-test, H0, what they ask, okay, I forgot that. Whether the true average stance duration is larger amount elder individuals than younger, which means mu1 greater than mu2. So HA I can write mu1 greater than mu2, right? According to my definition, according to my assumptions, mu1 is for average stance duration of older, and this is mu2 is for younger. So mu1 equals mu2 for H0. Your alpha is 0.05. Okay, okay, test statistic, it is very similar what we have done, x bar minus y bar minus delta naught. Here delta naught is 0, equals to 0, divide by s1 squared over n1 plus s2 squared over n2. Okay, square root. Let's simplify this, 801 780, this is 0. Okay, then 117 squared over 28, I'm just plugging the values, 16. Once you solve this, you will get 0.74. Now the question is, if you need to find this value from the t table, you need the degree of freedom, or let's say v. To do that, you cannot simply take it like n minus 1 or n1 plus n2 minus 2. No, this is not true. Okay, in this case, you have to find the degree of freedom using, you remember there was a giant equation, s1 squared over n1, s2 squared over n2 squared, divide by this one, s1 squared over n1 squared plus s2 squared over n2 squared, is divided by its n minus 1, is divided by n2 minus 1. I think this is, yeah, this one. Do you remember this one? Then always round down. For an example, if you have okay, I'll get the exact answer. This is 14 point, sorry, 41.868. So you have to consider it as 41. So your degree of freedom is 41. Clear, always round down. Go to the T table and find this value. T as alpha is 0.05, degree of freedom is 41, value is 1.8683. Okay. So you can see this value is 1.86 greater than this value. Okay. Tcal less than T 0.05 41. This is one tail test. Okay, one tail test, right tail test, one tail, right tail test. So do not reject. Clear? Part C, I think I'm not going to do that. You can find that particular equation and do that. Okay, I don't have enough time. It's almost 45. So to find this, you have to use the equation x bar minus y bar plus or minus t alpha over 2 degree of freedom times square root of 1 is s1 squared and 1 s2 squared over n2. Okay, using this you can find out what is the confidence level or confidence interval. Here alpha is 0.1. Okay, this is chapter 8. Yes, chapter 8.